before I go, let's just go on with the syllabus. Okay, I think that is very important. And the first unit, as in all of your subjects, will basically be a recap of some of the things which you might have already studied. Okay, so whenever you are talking about a circuit and you are going to solve any kind of problems, okay, based on electronic circuit, you need to know some theories, and Thevenin theorem and Norton theorem is something which we are going to visit. So these are all nothing but the network theorems, but then this is not exhaustive. There are other theorems also. So something like Ohm's law or finding out the equivalent resistance, capacitance, or inductor. This is something which is considered fundamental, something which you should already know. Okay, so every now and then we are going to see those things. Okay, and then we are going to solve it. Okay, might be directly, and then I expect that you might be already knowing these things. Okay, but then I'll try to explain and make it as simple as possible. That's very important. And then we're going to talk about ohmic and rectifying contacts. Okay, so basically whenever you are having any kind of electrical system, let's say even a thermocouple, okay, you basically have some kind of contact between two different kind of wires. Okay, so whether it is a ohmic contact or a non-ohmic contact, that is very important. You are taking out an output from a circuit as an electrical signal, what kind of contact you should be having, all those kinds of things. Okay, so it's basically going to be very introductory. Okay, there are of course more details, but then we are not going to do that because it is expected that you know some of these already. Okay, PN junction is something might be which is one of your favorite topics, because whenever we are talking about semiconductor, PN junction is something which we keep studying. Okay, so PN junction is there, and then applications of PN junction is there, and then there is something which is also called varactors. Okay, so varactors, if you have not heard about it, we are going to study that. Okay, and then Zener diode, already known to you. We are just I'm just not going to give you a theory. Okay, it's like, if I'm not wrong, many of us have come across this. Okay, whenever there is a class on electronics and there is something on Zener diode, Schottky diode, or light emitting diodes, okay, the teacher concerned will give you a long note and say that it is self-explanatory, you can go and just study this. Okay, so well, I like to just avoid that. Okay, I'll keep a circuit diagram. Okay, or might be the symbol, or might be the circuit involved, or the component involved, and I'll try to just explain it. Okay, and then you can definitely write it in your own words, because these are the topics which is going to be more or less a bit repetitive. Okay, but then some of the points you might have forgotten, so it's very important that we revise that. So Zener diode and something like Schottky diode, you might have heard about Schottky defect and all. Okay, everything is going to be there. Okay, Schottky defect might be a part of your experimental technique topics also. Okay, and then there is something which is called the tunnel diode. Okay, and tunnel diode is something which is like tunneling of the electrons to come out and basically contribute to the circuit. Okay, having an electric power supply. And then of course the light emitting diode, something which is a revolution, okay, in the power industry, because it has helped us to save a lot of electricity. So light emitting diode. So this is actually the first unit where we're basically going to study which we already know about. Okay, but then this is going to help us to understand the later chapters better. The second unit that we are going to talk about is on transistors. So let me tell you, the transistors is basically something like a three junction device, right? You already know it, and you know about active and passive elements. So transistors usually comes under the passive elements, okay, and not the active element. So it is very important that you study about transistors. And when you talk about transistors, there are something which are called the H parameters and all. Okay, so these things need to be studied in more detailed way. So probably we'll have some longer derivations, and you have no other way out but then basically to study these longer derivations. Okay, it's very important, each parameter analysis. Okay, and then how you bias a transistor, the input should be forward bias, the output should be reverse bias, and all those stuffs I think is already known to you, but then we are anyway going to do it. Okay, because these things we need to understand the each parameter analysis. And then there are also AC models. Okay, so basically you have an AC power supply operating a transistor. That's something which we're going to look into it. And then amplifiers, I think amplifier is one of the most important topic, because whenever you are going to talk about something like a signal, and if you're interested in amplifying the signal, you have different kinds of amplifiers. Okay, so even if we're talking about something like operational amplifier, it has got a specific job. Okay, similarly we have got these voltage amplifiers and all. Okay, so these all deals with transistors. Okay, you have got the Darlington pair. Okay, and then field effect transistor. Okay, FET is actually nothing but something which is frequently used in any kind of electronic circuit that we use nowadays. Okay, very important. JFET, junction and field effect transistor. Okay, biasing in ohmic and active regions. So all those kinds of stuff we are going to see. Okay, And then MOSFET, okay, deals with metal oxides, okay, and then thyristors and SCR crowbar. So these are all actually dealing with transistors. The second unit is on transistor. Okay. The third unit is operational amplifier, and this I think the topic you might have studied in your undergraduate level, but then that was not that much detail. Now we have an entire unit based on the operational amplifier. Okay, so a lot of things here are new to you. Okay, so I'm not going to just talk about each of these topics, but let me just tell you, we are going to go into more detail of that. We're going to look into more of different kinds of operational amplifier and how does it work, okay, and different kinds of parameters associated with it, okay. Something like inverting and non-inverting terminal, you already know about it, okay, but we're going to just go into more detail of that, okay. And then what is the basic characteristics? So basically what happens is in electronics, okay, or whenever even you tell you about electricity, you basically talk about IV curve, okay. And whenever you have got any kind of electrical component, and if you actually are able to find out the response that it gives with respect to a particular voltage applied, you're going to get some kind of IV curve, and that IV curve can give you a lot of information, okay. If you're talking about, let's say for example, a solar cell, okay, if you're talking about the IV characteristic of a solar cell, you actually can easily say what is the efficiency, how much current it can produce, how much voltage is needed, and so on, okay. So in terms of electronics, okay, this graphical representation gives you a lot of information. So probably we are going to look into these kind of IV graphs more and more, okay. Even in your transistor also, you cannot do away with IV characteristic. That is very important. So what we are going to do is we are going to study about IV characteristics of even op-amp, okay, op-amp amplifier, okay. So that is also there important. And then IC, okay, integrated circuit, how we are exactly using the op-amps in the integrated circuit and all those things, okay. And of course there is some combination of op-amp that can be used to actually study it, okay. That part is also there. So that is your third unit. The fourth unit is actually digital electronics. So digital electronics, when we talked about the adder function, let's say 00 give you 0 and the 101 gives you 1, okay, and so on, okay, the NOR gate, the NOT gate, the AND gate, okay, the OR gate, and so on. So this is something which you have already studied in your degree, okay, undergraduate level. Even nowadays, even in 12 also it's there, okay, towards the end of your physics chapter of class 12, if I'm not wrong, okay. So the thing is, we need to go further than that. So how is the application usually done, okay? And then something, if you might have heard about, is the JK flip-flop, okay? Those are nothing but practical setups that are being used in any electrical circuit to make the system more intelligent, okay? So if you talk about something like artificial intelligence, okay, which is like is booming nowadays, but then if you don't have a circuit to actually give instructions to the system, you really don't have any kind of artificial intelligence. So these kind of circuits actually are dealing with these kind of designs, okay. So if you talk about a digital circuit, you cannot do away with digital electronics, okay. So that is very important, okay. So the adder function and then or function and so on, okay. So these things are something which we're going to look into the fourth unit. And the final unit is something which is a bit alien to me also, because during my time I didn't have anything with microprocessors in the syllabus, but this has been included, and nowadays most of the advanced system or advanced syllabus is basically having those inclusion, okay. So whenever you're going to purchase a system, let's say a laptop, okay, and you're talking about processor, you look into it whether the processor is powerful enough, okay. So 8085A microprocessor is actually one of the initial microprocessors, okay, developed by Intel. They are highly working on these things, okay. So if a processor is good, that how fast you can actually do a calculation. So those kind of ideas that a computer can do a million calculation in maybe a 10 minutes, but for a human to do it, it might take around 1 month, 2 months, okay. Those things has become possible only because of microprocessors. So I guess microprocessor is important. Microprocessors, more detailed studies are being done for the students who are doing MSc in electronics, or those who are doing engineering in electronics, or electronics and communication, electronics and instrumentation, and so on, okay. But then we also need to know a bit about it, and that is what is being done in this final unit. But most probably this is the unit which I might not be taking up, okay. We will soon communicate with you with that, okay. We have already sir is already there, he'll be taking the classes, but okay, this is something which we are also going to do. So these are the 5 units that we have on, and today what we are going to do is, and this is our first class, just not going to make it too complicated. We're just going to go on with the first, start with the first unit, okay. Now, why do I discuss the syllabus, because you have to know that what are you going to learn in this course. That's very important. Okay, and then if you're going to learn in the course, it's very important that you know what kind of book you should follow. So you see, electronics, you can take up a book, whatever you studied in your undergraduate level, and you will see that most of these things are already there. The only thing is you might not have studied it during your undergraduation. Okay, so if I'm not wrong, many of you might have heard about DC tile and you might have followed that book. Okay, but then somehow I found a lot of printing mistakes there, and then sometimes I found a lot of steps being skipped and I get a bit confused. So what I preferred was VK Mehta, S Chand. Okay, so if you take up an electronics book published by S Chand, those books are actually quite good. No doubt, there is always this that Estrand is basically nothing but a copy of some book written by some foreign writers. But let me tell you, some of the books are pretty good. So if you just look into VK Mehta, it will be good. I don't know whether a soft copy is available or not, but then you can just check for it online. Okay, if it's not available, you can buy it. Okay, it's affordable. I don't know what's the price now, but I am using VK Mehta, but and you can always look into it. Okay. As far as online lectures are concerned, I will be anyway uploading these lectures. But if you want to just follow some other lectures, I think NPTEL has got some lectures. Frankly speaking, some of the lectures doesn't entertain much, but then the concept is well dealt with. Okay, you can understand it clearly. But then there are some foreign YouTubers who are actually uploading very good lectures on electronics. So electronic is a topic on which you will get much more lectures compared to any other topic in physics, because electronics is there for MSc electronics, engineering and all. So there is more scope of people making videos on that. Okay, so you can find out those lectures and try to understand it better. And I'm sure that many of us have this confusion of how to exactly solve a circuit, or sometimes we ignore electronics, somehow just do it during our undergraduation. But then I think it's high time that we just need to study that better, because if you're going for net exam or gate exam, electronic forms a very important part, and it's very, very scoring. Okay, so that's very important. So, the first unit, if we actually start with, and we want to talk about the basics, what we have is something which we call as the network theorem. Okay, so I'm just going to talk about two network theorems here. There are a number of theorems, but then two of the most important network theorem is Thevenin theorem and Norton theorem. Okay, so what happens with Thevenin theorem and Norton theorem is that whenever we are going to have a circuit, one of the important thing that we want to do is simplify a circuit. Okay, so that is very important. So if you want to just simplify a circuit, it sometimes becomes a bit complicated, because there are a lot of components that are being present there. So if you have a circuit, think about it in this way. Okay, I'm trying to simplify it as much as possible. Think about it in this way: you have a circuit, okay, and then you have got one variable component, and you want to actually get an output. Let's say you want to get the output voltage, and you have got one variable component. Now what is a variable component? Might be a variable resistor. Okay, you have it, and if you vary, the output voltage keeps on changing. So every time you want to do any kind of calculation, it becomes complicated, because every time you change the resistance, the variable parameter, every information in the circuit changes. So what is the easiest way out? The easiest way out is, whatever is not varying, we will take an equivalent of that. So if I have got a number of resistors, I'll take an equivalent of that resistance. If I've got a number of voltage sources, we'll take an equivalent voltage source. Once that is done, then I can connect the variable part and then do my calculation. Then the calculation becomes very simple. Okay. So the idea is very simple behind these theorems or network theorems of Thevenin and Norton. Okay. So whenever you do any kind of theorems, if you just straight away jump into the practical example and just solve it for exam purpose, you don't really appreciate the fact that why it is important. Okay, and that is what I'm saying exactly. Okay, so I'll just start with the Thevenin theorem, and this is all theory. Let me just read through, and then I'm going to go into the practical picture. Okay, so if you all remember, whenever you are dealing with any kind of, let's say, transistor, okay, field effect transistor, junction transistor, an amplifier, okay, a voltage regulator, the circuit is very complicated. Okay, if you want to just simplify it, we can actually use some kind of theorems into it. Okay, that's very important. That doesn't mean that in the original circuit you can actually change anything. Okay, it's not that. But the thing is, if it's a complicated circuit, I can make it a simplified circuit on paper and then look into the result more easily. Okay? So Thevenin theorem. Let's just read through. Any two terminals of a network, okay, composed of linear, passive, and active circuit element may be replaced by an equivalent voltage source and an equivalent series resistance. So as I said, if I have a complicated circuit, okay, if I don't have any voltage source, I'm definitely not going to get any kind of output, okay. So most of the circuit will definitely have some kind of active element, okay. So in simple words, what do you mean by active and passive? So active might be something which can generate its own power, okay, or it can actually power up a circuit, okay. So even if an amplifier, it is also a active element, because indirectly this is actually going to have an impact on the voltage. It's an amplifier, so it's basically going to amplify a signal, right? So definitely it's a passive element. If you consider something like a capacitor, inductor, resistor, these are all passive elements, okay? These are not active elements. So you have a circuit consisting of active and passive elements, and then you want to actually have an output. Now output is always taken across two terminals. So when you take out that output, that is something where we can actually use the Thevenin theorem to actually simplify the things. Okay. So what we do, we actually find out only one equivalent voltage and one equivalent series resistance. That's all. Okay. So does it mean it will have only resistance? That's not true. Okay. We can actually have a capacitor and an inductor. Okay. And the corresponding reactance can be considered, made together, and then you can actually get the equivalent circuit. Okay. So the voltage source is basically equal to the potential. Okay. So marker कहाँ गया? Okay. Okay, so the voltage source is actually the potential difference between the two terminals. Okay, so whenever you're basically talking about any kind of circuit, what is the important part is that if it's electricity or if it is electronics, we need the electrons to flow. So whenever we want the electrons to flow, we should actually apply some kind of potential difference. Okay, so that's your voltage source. Okay, and what is the series resistance that we are talking about? The series resistance is actually nothing but the equivalent resistance. Okay, when we look into the two terminal port with all the power sources within the terminal pair inactive, what does this mean? You want to find out the equivalent resistance. So you just want to know that what is the total resistance of the system. So at that point of time, you really don't need to know the effect that voltage has on this resistance. So what we do is we remove that voltage source. Okay, even if there is a current source, we'll remove that current source, and we will just have the resistance plain and simple, and then we will start studying that. Okay, once we study that resistance, we can actually get the equivalent resistance. So that is what we are going to do, okay, in Thevenin theorem. So what we're going to do is we're just going to take an example and trying to understand it better. But before that, let me just show you this circuit. So you have got a black box, and by the term it black, it means that I'm really not sure what are the components inside. Okay, what are the resistances, what are the voltage sources, and so on. Okay, so when we're solving it, we definitely know it. Okay, but then if something is not known, we basically call it as a black box. So if you want to just find out the equivalent voltage that is there across this particular circuit, we are actually going to just write down an equivalent voltage source, which is VTH. Okay, and then we are going to look into all the resistances, solve them. We will know about parallel and series combination of resistance. Okay, we are going to use those ideas. Okay, and then we are going to simplify the circuit, and we are going to get just one equivalent resistance. Okay, so this is where we are talking about one equivalent resistance. So that is the resistance, equivalent resistance. That is the Thevenin resistance. Okay. The fundamental difference between Thevenin and Norton theorem is that there we're talking about voltage source. In Norton theorem, we are going to talk about current source. Okay? So whenever you look into a circuit, there are different components. Okay, there are dependent components, there are independent components. Okay, and then many of time it does happen that we don't know the notation. So as we go along with the syllabus, we are going to look into different kinds of notations. Okay, so I'll make sure that I explain all the terms and all the notation that we are basically using in any kind of circuit. Okay, so how do I find out the voltage? That's the first question. What we do is we are actually going to replace this. Maybe I should take a pen. So my background is too bright, so sometimes I'm not able to figure out where is the marker. Okay, so we basically will replace this voltage source with short circuits and current source with open circuit. So let me just give a brief on this. Okay, I think you already know about short circuit and open circuit. So if you basically have a circuit, okay, if you basically have a circuit something like this, let's say I have this, okay, and then I have got some resistance in between. Okay, my mouse is not placed properly. ऐसे हो गया, ठीक है? Just place it. So you have it, okay. So you have a resistance in between, and then you have it here. Okay. So you know, whenever there is a flow of charges, this resistance is going to oppose that flow of charges. If there is any kind of voltage on this side, okay, after it crosses this, the current, there is going to be basically a voltage drop that is going to be experienced on this end, right? So what happens is if I remove this resistance with, let's say, a copper wire is can be considered to be practically having very low resistance, not zero resistance. It's very difficult to say zero resistance. So zero resistance is only possible for something like a superconductor. Okay, so we do have a conductor, and we say that it has got a very low resistance. So ideally, it should be zero resistance, but you know, ideally and practically are two different things in electronics. So it's not practical. It's a practical example. We can take a copper wire, and then you can remove that resistance, and that is nothing but a short circuit. Okay, so we're basically directly connecting it without putting any kind of component in between. Okay, that is a short circuit. And you know already about open circuit. So if you look into this particular diagram and you look into A and B, okay, you know that between A and B nothing is there, so that means the current cannot flow. Okay, so basically you cannot have any kind of current flowing between these two circuits, right? So if there is no current flowing between A and B, okay, that means it is having infinite resistance, and that is what we call as the open circuit. So I think these things are known to you. So let's just take an example to understand Thevenin theorem, or to revise Thevenin theorem. Okay, so if you just look into it, you look into the circuit, okay, carefully. And the aim in this particular example is actually to find out the equivalent voltage and the equivalent resistance. Okay, so if you just want to find out the equivalent voltage and equivalent resistance, what you're going to do is what Thevenin theorem talks about. Okay, so what is the aim? You see, you have to find out. So you have to find out the voltage, okay, across the terminal A and B. Okay, and then this is written to be 2 ohm. Okay, it's not mandatory that it should be 2 ohm. This might be the variable parameter. You might be having a variable resistor there. So if you know a symbol of a variable resistor, you know you can actually draw a resistor. Okay, you can draw a resistor, and then you can actually put an arrow like this. Okay, and that will be a variable resistor. Okay, so if you have a variable resistor, let's say it's denoted by Vx. Okay, you know 4 ohm, 6 ohm, 12 ohm, and the 30 volt does not change, but then the Vx value changes. So the aim is to make a circuit where we have a one resistance, one voltage source, and then we can actually find out what is the current flowing in the circuit, and that is what is Thevenin theorem is all about. So for that, what will be the first step? It's very simple. We are just going to remove this Vx now. We are just going to remove this Vx. Okay, so because we are going to find it out across A and B. Okay, if you just want to find it out across A and B, what we do is we just remove this part, and if we just remove this part will actually become an open circuit system. Okay, and then before I really go into the calculation, let me just give you a very simple idea that whenever you are actually having any kind of voltage source because of which the current will flow, the electrons will flow. Okay, you can go from the minus to the plus. So that means it is going from a lower potential to a higher potential, right? And then if this is 30 volt, the potential at this point will also be 30 volt. Okay, potential. So what is the potential here? Let's make it 0. So that means the potential difference across this is 30 volt. 30 minus 0. And that is why it is written 30 volt here. Okay. So practically or ideally, whenever you have any kind of circuit, I think you have already studied it in your, let's say, operational amplifier or transistors when you studied in your undergraduation, that they ground it. What is the reason? The reason is when you ground out a particular part, that region the potential is 0. Okay, and then you can actually have some potential on the other end, and then there will be a potential difference. If there is no potential difference, the current does not flow, the circuit doesn't work, it doesn't operate, and that is why grounding a circuit is very important. So even if a diagram doesn't show ground and they said that there is a potential difference, you can expect that actually it is grounded. Okay, it is expected that it is grounded. If you don't ground it, you don't get that much of difference. Okay, it's very important. So what happens here is we have got a 30 volt, so that means here it might be 0 and here it will be basically nothing but 30 volt. Okay, so you can ground it at this particular point, and then across entire length of this, because there are no other electronic component here, we basically have the potential as 0. Okay, but here it's different. Here it is 30 volt, and then as soon as we cross this 12 ohm, there is a potential drop, and that potential drop is V minus IR. So if I know the current, I know the resistance, I can subtract it from this 30 volt. I will get what is the potential drop on this side. Okay, so this is something which is more basic. I'd like to just explain this now so that you are like confident about approaching these kind of circuits. Okay, so now what happens is the current will flow and it won't flow along this direction because current will always take the path of minimum resistance. So if it goes along this path, it's going to experience infinite resistance here because it cannot flow. There is no path. So that means practically we can say this is the only circuit which is working now whenever we remove this part. So if this is the only part which is working, okay, this is the only part which is working, okay. I should go to the previous slide. Yeah. Okay, so this is the only part that is working. Okay, and this part there is no current flowing, so we can just ignore this 4 ohm resistance. So if we just ignore this 4 ohm resistance, can we find out what is the current? Okay, it's very easy. We have got a simple circuit with voltage and two resistances in series. So what is the resistance here? You see, this is the current flowing. There is no current division here because current won't flow here. The entire current will be here. So if here it is I1, this part also it is I1. So that means 12 ohm and 6 ohm are connected in series. So it's 18 ohm. Okay. And what is the voltage? 30 volt. Okay. So if we just want to find out the current, okay, we can just find out what is V is equal to I into R. Okay. And then you can easily find out what is the current. Okay. So once we can find out the current, we can actually find out what is the voltage across AB. Okay, if we talk about this as A and this is B, and if we say that no current flows across this, along this also it will be the same voltage. So we can just take A and B across this also. Okay, okay. So we can also take A and B here. So this can be A, okay, and this can be B. So AB across this or across this is the same. Okay. And what is the potential drop across this at this particular point? What is the potential drop? That is the aim. Okay, so this potential across AB, okay, is nothing but 30. Okay, this will be nothing but this value of 30 minus the potential drop across this. So what you can do is, this might be a task for you. You can find out what is the current flowing across this circuit. That would be nothing but V is equal to IR, so is equal to R divided by V. So that will be nothing but 18 divided by 30, right? Something like that. So if you do the calculation, and you can put what is V is equal to I, you find out what is I, and then you can just take I into R. So that means that current into resistance minus 30. That will be the potential drop here. Okay, that is the value. But then there is an easier method, or there is a shortcut method of this, because you want to find out what is the potential drop across 6 ohm resistance. You can straight away do it in this way also. You can simply take 30 into 6, because you are measuring the resistance or the potential drop across 6 ohm resistance. Okay, and divided by the total resistance of the circuit. So the total resistance of the circuit is 12 plus 6, which is nothing but 18. You can do it this way, or you can simply find out V minus IR. Okay, where R is nothing but 12 ohm. Okay, and V would be nothing but 30 volt, and R is already there, but I you have to calculate. So you can do it that way also. But this is the better way because this is easier. This method you might have used it. Okay, so what happens here is that if you have a circuit which has got a number of resistances, you can find out the total resistance, put it at the bottom, and then take the voltage of that particular circuit, multiply it with the resistance across which the voltage drop has to be measured, and then do the calculation. Okay, this is actually very important if you want to do some sums fast. So you just do this calculation. This will be nothing but 10 volt. So what does it give me? It gives me that the equivalent the equivalent voltage for this circuit is nothing but 10 volt. And this 10 volt is nothing but the Thevenin's voltage. Okay, so this is very important. So this entire circuit has a lot of stories to tell, and this is something which you have to revise. That's very important because I think it has been a long break since you have touched electronics. So I hope that all of you can just go back and just revise a bit whatever you studied. Okay. So I found out what is the equivalent voltage, and that is nothing but 10 volt. The next is, how do I find out the equivalent resistance? Okay. So I'm concerned only about the resistance. I don't need any kind of source. So here also I'm going to do the same. What I'm going to do is I'm going to just remove the output voltage. Okay. I'm just going to remove the output voltage. Okay. So maybe I can just go back to the original circuit. Okay. So if you just go back to the original circuit, what I'm going to do is I'm going to remove this part to find out the equivalent resistance, and I'm going to omit this part also. That means this part I'm going to short circuit. If you remember, I told you here that if you have the voltage source, you short circuit it. Okay, so if you have the voltage source, you short circuit. But if there was a current source, something like this is a current source, you will open circuit. Open circuit means you are just going to not connect the two ends. Okay, so I'm just going to short circuit the voltage source. So that means I'm going to just remove it and connect it by a simple wire. And this part I'm just going to remove. Okay, and then I'm going to find out what is the equivalent resistance. So, whenever you are going to find out the equivalent resistance, it is always preferable that you start from the open end. You start from this end and calculate the equivalent resistance. So there is one resistance 4, okay. There is one resistance 4 ohm, okay. And then this is connected to a set of two different resistances. So what we have to do is we have to see that this 4 ohm is actually having no current division, but at this particular point, which is basically called the principal node, if you remember, the principal node where more than two components meet. So there are 4 ohm, 12 ohm and 6 ohm, all three of them meet at this particular point. So this is a principal node, okay. This is a simple node. This other end is basically a simple node because here you have got one end of 12 ohm and one end of 6 ohm. So this is a simple node, but this is a principal node. So at this particular principal node, you see that the current gets divided. Some part will flow along this and some part will be following, going along this. Where do you get that current? It's not that you're getting a current, you're just imagining it, because whenever you are trying to understand whether a resistance is in series or parallel, okay, if it goes have the same current throughout, it will be in series, but then if the current gets divided, they are in parallel. Okay, so that is the basic idea. That's why I'm explaining it in this way. So what we have is 6 and 12. So they are in parallel because the different current is flowing across this. So 12 and 6 are in parallel, which is connected with 4 ohm resistance. So parallel, 1 by 12 plus 1 by 6. Do your calculations, and then the equivalent resistance that you're going to get is 8 ohm. So this circuit has got three different resistances and one voltage source. What we did was we just found out one equivalent resistance, which is nothing but 8 ohm RTH, and then we found out one equivalent voltage, which is nothing but 10 volt. Okay. So once we get this, we can actually have the Thevenin equivalent circuit. So this is called a Thevenin circuit. The previous one was not a Thevenin circuit. This is a Thevenin circuit because we actually have simplified the circuit and found out the equivalent voltage and equivalent resistance. Once that's done, you can do any kind of calculation. Now you can have a 2 ohm here, a 10 ohm here, an 18 ohm here, but the calculation will remain very simple. But imagine the original circuit. You have to every time you have to find out the equivalent resistance. Now you don't need to do it. Just add up this 8 and 2, you get 10, and you find out what is the current in the circuit. Okay, if you want to find out what is the voltage, okay, across AB, that means across this, what is Vx? Vx is something which is unknown. You can simply find out Vx is equal to I into R. Okay, so you know what is R is 2m, and you can find out I for the circuit using Ohm's law. Then you can do the calculation. Once you do the calculation, your answer will be 2 volt. You can do it on your own. Okay, I'm not going to do this. But then, of course, there is an easier way. You can always take the voltage, total voltage, and then multiply it with the resistance across which you want to measure the voltage, divided by the resistances in series. So it will be 2 plus 8. So you get 2 volts. So that's the same answer that you're going to get. Okay. So there are some specific methods that we should all know, and this is one of the methods that is very important. Okay. So I suggest that please go through this Thevenin theorem and Norton theorem, okay, and all of you will have a much better clarification on this, okay. So I will just leave you with this, okay. You can just take a screenshot on your mobile and just try to solve it, okay.